Okay, Assalamualaikum and very good evening to all of you. Welcome back to our class. In today's session, I will discuss about the example, okay, exercise number 10, okay, which is strongly related to example 1.8 from the module, but I will adjust some value so we can do it together. Okay, this is still the design of shear reinforcement. However, we have to consider for the flange section. Okay, in exercise number 8 and exercise number 9, we consider for rectangular section. Okay, so now let us start. Exercise number 10. Okay, I give you the parameter, the new parameter to be set. Okay, you may refer later to this example from the module. However, the new parameter is given as exercise 10. Okay, still simply supported beam flange. However, okay, you can refer to this figure later. However, the span I want to use L is equal to 6.0 meter. The UDL, the ultimate UDL is equal to 120 kilonewton per meter. The size of beam, okay, the BF is equal to, okay, BF means flange, okay. BF or B is similar, okay. And the BW is equal to 2 to 5 mm. Okay, how about the HF? HF is equal to 150 mm. And the D is given here as 500 mm. Okay, and then the AS prime is equal to 2H12 or equal to 226 mm square. The AS is equal to 6H20 or equal to 1880 mm square. Okay. And then the concrete class is still used. We use FCK. Okay, FCK is equal to 30 Newton per millimeter square, and FYK is equal to 500 Newton per millimeter square. Okay. So the first solution is we determine the. Okay, I hope you can okay. You can just refer to this figure. Okay, and as the solution, oh sorry. Okay, the solution. Okay, first we have to determine the design shear force. Okay, since our section is a simply supported beam, so we can simply use the formula VED is equal to WL over 2 equal to 120 times 6, okay, over 2. So what is the value? Okay, what is the value of VED?
360.
Okay, it's 360 kilonewton. Thank you. And then we check for, just use similar, we check the concrete strut capacity. V are the maximum. Okay, use the equation of 0.36 dot BW dot D dot FCK times 1 minus FCK divided by 250 and divide by cotangent theta plus tangent theta. First, we check for theta. Theta equal to 22 degree. So what is the value of cotangent theta? Cotangent 22 degree is equal to 2.5, and tangent theta is equal to what?
0.4.
Okay, good. 0.4. So what is the VRD maximum? So it's equal to 0.36. Okay, BW we use 2 to 5, and then times 500 times 30 times 1 minus 30 over 250 divide by 2.5 plus 0.4. So what is the VRD max? This is 500, okay? Okay, any answer?
370.
370, okay.
368.
368 point something kan? Okay, so it's okay lah. So 369 lah, okay. Point something tu you bulatkan je lah, okay. So this one is larger than our VED. So what is the conclusion? Do we need to check for theta 45 degree?
No.
No, okay, because it's already larger than VED. If VED is larger than this one, so we have to check for the theta 45 degree, and then we have to, if the value of VED is in between, so we have to find the value of theta first. So we design for theta equal to 22 degree. So directly we can design for shear reinforcement. Okay. So ASW over S. Okay, we use let's say we use, okay, let's say we use H8. Okay. So ASW is equal to 101 mm square. So ASW over S is equal to VED divided by 0.78 D times FYK times cotangent theta is equal to 360 0.78 times D is equal to 500 times what is the value of FYK? Also 500 times 2.5. Okay, what is the value of ASW over S? Any answer?
0.74.
0.74. Okay, thank you. 0.74. So what is our spacing? Is equal to ASW over 0.74 is equal to 101. Okay, what is our spacing shall be?
$100.
The answer first.
136.
Okay, 136 mm. So the conclusion we use H8 100. 100 is okay. Okay, 125. Okay, 125. 100 is okay. 75 also okay. But we can save our budget, okay, by using the larger value. Center to center, this is the near support. Okay, and then we check our S maximum. S maximum is equal to 0.75 D is equal to 0.75 times 500 is equal to 375 mm. So larger than 125. Larger than 125. So okay lah. Okay. And then what to check? Okay, we design the minimum link. Okay, just similar process with the rectangular section. Design minimum link. So ASW over S is equal to, let's say, UCH8 ASW 101 mm square 0.08 BW times FCK square divided by FYK equal to 0.08 times 225 times 30 500. Okay. What is the value? This one, yeah.
.2.
0.2.
0.2, okay. Okay, 0.2. Okay, so what is the spacing? ASW over 0.2 is equal to 101 divided by 0.2.
.505.
505, thank you. 505 mm. So what is the spacing should be used? H8
375.
375, okay. 375, okay, but because 375 is the maximum, however, in the clause here, okay, should be greater 75. 375 is the maximum, okay. So we can use 375, okay. Okay, so we can use 375 or lower value, okay. So 375 mm center to center, okay. So because it's still not reach the limit, okay. Okay, still equal to S maximum, so okay. And then the capacity, shear resistance of minimum links shall be V minimum equal to AS W over S times 0.78 times D times FYK times cotangent theta. So it's equal to 101 divided by 375 times 0.78 times 500, also 500 times 2.5. Okay, what is the value of V minimum?
Uh, 131.
131, okay. So equal to 131 kilonewton. Okay, so what is the distance of X? X is equal to 360 minus 131 times distance over 2 divided by 360. Betul kan? So, answer Any answer? X.
1.9.
1.9
Ah,
divided by 360. 1.9, okay, 1.9 something lah, okay, 1.9 meter. Okay, so however, in this case, if we consider flange, we must provide the transverse still in the flange. Okay, let's say see this clause. So this one, okay, you can refer to this notes, page slide number 18. We must okay, longitudinal reinforcement should be provided as you see, as this one. Okay, okay, if you want to see clearer, so this one. Okay, we must provide. Okay, if we consider flange for our shear reinforcement, we must provide this steel. This one. Okay, this is the transverse steel in the flange. Okay, this one. Okay, the red color. I hope you can see. Okay, so and this is okay, this one. This is the AST, and then this is the spacing ST, the distance. Okay, so how to do is okay, the longitudinal shear stress. Okay, the longitudinal shear stresses are the greatest over a distance okay, measured from the point of zero moment. Okay, so the okay, delta x is equal to 0.5 L over 2 equal to 0.56 over 2 equal to 1.5 meter or equal to 1,500 mm. Okay. Okay, next, the change in moment over distance delta x from zero moment okay, change of moment is equal to WL over 2 times L over 4. You can refer to the module, it's okay. WL over 4 L over 8, okay, or simplified by 3WL square over 32. So equal to 3 times 120 times L square over 32. So the answer is equal to okay, any answer for the delta moment?
405.
Okay, 405. Thank you. Kilonewton meter. And then, oh sorry, I Sorry, out of page. Okay, so the change is in longitudinal forces. Okay, the change in longitudinal forces delta FD is equal to delta M divided by D minus HF over 2. Okay, multiply by the B minus BW divided by 2B. Okay, so equal to delta M is equal to 405. 405 times 10 to the power of 6 divided by 500 is our D minus 150 over 2 multiply by 600 minus BW is 225 divided by 2 times 600. Okay, so what is the value now? Okay, any answer, class?
298.
Okay, good. Siapa yang jawab tu ya?
Adam.
Okay, Adam. Thank you, Adam. Thank you. 298. And then the answer is, okay, the longitudinal shear stress V, okay, V huruf kecil ya, V huruf kecil, VED, tadi V huruf besar, sekarang delta D divide by HF dot X, delta X sama dengan, okay, 298 kali 10 kuasa 3 bagi dengan 150 kali dengan 1500. Okay, bye. Okay.
1.32.
Okay, 1.32 Newton per millimeter square. And then you check with 0.27 FCTK is equal to 0.27. FCTK is you refer to this table. Okay, you refer to this table for FCTK. Yes, this table. Okay. This one. Okay, row number 1, 2, 3, 4, 5. Okay, just below the FCTM. Okay, FCTM is for the calculation of AS minimum. And FCTK is here. Okay, it's for concrete grade 30, the value is this one. Okay, 2.0. Okay. So 2.0. So it's equal to 0.454 Newton per millimeter square. Therefore, the VED greater than 0.27 FCTK. So, transverse steel reinforcement is required. Okay, and then we calculate the strut capacity. Okay, this is quite challenging. Okay, we determine the strut strut capacity in Flange. Okay, V are the maximum. Okay, for the Flange, this is the equations 0.4 FCK 1 minus FCK divided by 250 over cotangent theta plus tangent theta. So just but however for the compression flange, okay, of course this one, okay, the flange in compressions at the midspan, okay, we talk about midspan. Here is the compression, okay, the top. So for the compression flange, the theta is between, okay, sorry, okay, the value of theta for this case is between 22.6 24 to 26.5 degree lesser than 45 degree. Okay, so we check for, okay, for theta equal to 26.5 degree, cotangent theta is equal to 2.0 and tangent theta is equal to 0.5. So you calculate, okay, based on these equations, VRD max is equal to 0.4 times 30. Okay, 1 minus 30 divided by 250 divided by 2.0 plus 0.5. So what is the value of VRD maximum? Okay, anybody have the answer?
4.2.
Okay, 4.2 Newton per millimeter square greater than the VED. This one, okay, the VED we calculated before. This one, okay, this 1.32 is greater. So just like the rectangular beam, yes, just like in the case of rectangular beam. So we can conclude that we can, okay, greater than VED. So we can use theta is equal to 26.5 degree. If the value here, okay, if the VED, let's say our VED is 5.8, which is greater than 4.2, greater than VRD maximum for theta equal to 26.5 degree. So we must check for theta equal to 45 degree, and then we can find the value of theta again, just like the equations in exercise number 9. Okay, so for this one is simple, so we can skip the step. Okay, so we can proceed to the transverse shear reinforcement. AST divided by ST equal to VED times HF divided by 0.87 FYK cotangent theta. Our VED now is equal to 1.32 directly times 150 divided by 0.87 times 500 times 2.0. Okay, what is the value of AST over T? Any answer?
0.24.
0.24. Okay, thank you. 0.24. Okay, so you can, let's say you still use the similar, okay, as the link, use H8. So the ASW is equal to 101 mm square. So you can spacing, okay, spacing ST is equal to AST divided by that is 0.24 equal to, oh sorry, for this case the AST shall be only single, only 56 or 50.5 mm square. We use single because this one shear reinforcement, this one, okay, this one is single, not like this, the just like, okay, in the link, in the case of link, if you still remember this one, we use based on number 1 2, so we must select 2 here. They say 8 is equal to 101, but we select only 1, 50.3, let's say 50.3, sorry, so this one shall be 50.3 mm square. We only select based on one number of bar. Okay, if the case of link, if we have let's say this one, let's say we have three links here, so we select 1 2 3. Okay, so here in this case, so 50.3 divided by 0.24, what is the answer? Two one zero. Okay, 210 mm square. So what can you propose to use?
200.
200. Oh, spacing so spacing is mm. Okay, mm. Okay, so 210 mm. So okay, use to 200. Okay, you can use to 200. Use H8 200. Okay. Okay, 8 200. So okay, this table, okay, the for various bar spacing, you can see at the bottom here. Sorry ya, saya nak besarkan ni. Okay, this is the size of bar is 8, and then the spacing is 200. So for every 1 meter run, you got this one. Okay, so every 1 meter, for every 1 meter of this one, let's say this one, we must design for every 1 meter, just like the slab. Okay, this is 1 meter. Okay, for every 1 meter, the area is equal to, you refer this table, if you select 200, the area is equal to 251. Okay, 200 mm center to center, so AS T is equal to 251 millimeter square per meter. Okay, and then we check, okay, the final step, we check for minimum transverse, okay, steel area. AS minimum is equal to 0.26 times FCTM Okay, divide by FYK B times HF. Okay, it must be greater than 0.0013 B times HF. Okay, because we consider this area. Okay, this is our B now. Our B here is equal to 1 meter or 1000 mm, and this is our HF. Okay, this we design for this. This is the okay based on the area. So equal to 0.26 FCTM for concrete grade 30. We can refer to this table. Topic this one FCTM. Okay, this table for concrete grade 30, the FCTM is equal to 2.9. Okay, so equal to 2.9 divided by 500 times 1000. Okay, the B, the H is okay, must be greater than 0.0013 1000 times 150. So equal to any value for this one.
226.
Okay, 226 mm square, and then this one greater than 1. One and 5. Okay, mm square. So we select the minimum one. So if so as minimum is equal to 226 mm square per meter. So it our yang provide tadi we provide 251 greater. So it's okay lah. Okay. So T is equal to 251 millimeter square per meter greater than AS minimum. So it's okay. So the next step is as usual, you must check for additional longitudinal reinforcement. Okay, this one is similar to exercise 9 in 8 and 9. Okay, you just refer to that one to settle, and then you can finish. Okay, this is the situations. Okay, the situations if you consider the flange for shear reinforcement, where you have to consider the you have to consider the longitudinal shear stress. Okay, inside the flange. Okay, the flange here. So you must consider this one. Okay, this is this one. Okay, this steel reinforcement you have to consider. Longitudinal shear stress. Okay, changing in moment, changing in process. You have to consider this one. Okay, any question, class? For this part? Okay, if no questions, then that's all for our class today. Thank you very much for your attention. I hope you can settle exercise 9A to 9D and submit before Monday. Okay, thank you very much. See you soon. See you next week. Bye.